In this video, we will look at the steps needed to calculate some of the measures of dispersion that are in the notes and in the textbook concerning range, interquartile range, variance, standard deviation, and coefficient of variation. And we will do that for both the population and for a set of sample data. We'll start with the population and then move to the sample, and then after that we'll talk a little bit about the empirical rule and Chebyshev's theorem, and hopefully get an understanding of the importance of understanding variability, of having some measure of variability, and most specifically variance and standard deviation. For the range, I have some already made out here for you. The range is just the deviation between the maximum and the minimum value, so that's 6,000. The interquartile range, we've already talked about how to get the 75th and 25th percentiles, so those are done for us, but that's the difference then between the 75th and 25th percentile, 700. So you can see quite a bit of difference there, but do understand that this is only dealing with 50% of the data set. So you certainly would expect some difference. This is quite a big difference here, 700 versus 6,000, and that's mainly because of this value right here. So there's essentially one extreme value that's creating that large deviation. But again, you're still talking about 25% of the observations above this number here and 25% of the observations below this number for the to get from the minimum to the maximum there. So those are just pretty basic measures of dispersion, informative but very limiting. They don't use the entire data set, just certain values within the data set. So what we often use is something called a variance, and we need a mean first. So I've got the sum of the x values, 17,100, so I'm going to take that number and divide by 8, the total number of observations here. And so if you recall from the other video, that data set had a mean of 2137.5. So now the variance here will be looking at the deviation of the x's around the mean. So 1500 minus the mean, I'm going to freeze that. Something happened there. I didn't get my value here. Let's try that again. 1500 minus the mean, and I'll freeze that. There we go. And so then we'll just do that for every observation. And notice, you can kind of see here the mean is pulled up quite a bit because of this 7,000 value here. All the other values are below the mean, and this is the only one that's above. And that will vary, but the thing to understand though is that basically what we want is the average deviation around the mean. So why not just take these values and divide them by n, and we have an average. Well, the problem is the way the mean is set up, these values would sum to 0. So what we have to do is either take the absolute value here, which gives us another type of deviation measure that we're not going to use in 262. So we're going to instead square these deviations, each one of them. So we square them, and now when we add them up, we're going to have either a 0, which would mean that these are all constants and the mean was equal to all these values. So then these would be zeros and these would be zeros. That's typically not the type of data set we're dealing with. And so because we have variation, then when we sum these up, we would then divide that by n. So let's just put it over here. So So we'll take this number divided by n, and you essentially have a mean. A variance is a mean. So it's the sum of the squared deviations divided by the number of observations, and so there's your variance. And that would be the average, but it's the average of the squared deviations, which has some issues in terms of trying to interpret what's going on. So what we do is we take the square root of this variance, and so now we can look at this in terms of units, in terms of actual dollars, okay, instead of squared dollars. So we have a standard deviation of 1867.6, and that again that's in units, that's in dollars, so that makes it a little easier to interpret, and we'll get to the interpretation part later. So right now, just dealing with calculation, that's how you calculate the variance and standard deviation. And then the coefficient of variation is what we call relative measure of variation. Basically what it's doing is looking at this standard deviation relative to the mean. Okay? And so the standard deviation is basically about 87.37% of the mean. Right? So if you look at the lecture notes about coefficient of variation, you can see that its coefficient of variation is one way of looking at risk, but again, it allows you to compare data sets. Standard deviation is more of an absolute measure of variation, and it's not usually in a situation where you can compare from one data set to the other. Certain things have to happen concerning the mean and units and so forth that we're dealing with that would allow you to compare those different data sets. The coefficient of variation, you don't have to worry about that. You're looking at it as a percentage rather than in terms of units, and so you could compare this versus another data set of from another region. So then how would looking at a sample data set, how would that differ in terms of what we have to calculate here? Well, let's go to the sample data set that we used in the measures of location. I've got quite a few of the parts done here since we've already done them previously here. So I've got the 75th, 25th percentile, the mean, the range, interquartile range, and so forth. So those are all calculated just like for population. Even over here, you've got 2100 minus the 2013.75, and you get a difference of 86.25. You square that, and you do that for all the values, and then you sum up the squared deviations. Okay, so that's what we have here. And here's where things start to differ. So if this was all the data I cared about, that was the population, then I would just simply take this number, divide it by 20, and I've got myself a variance. But what I want is I want a measure that I can depend on as a measure for a much larger population. So remember, this is a sample, and there are actually over 4,000 available loans that we could have picked the values, and these are only 20 of those. So I want to try to come up with a variance measure that gives me a representation of the entire population of over 4,000. Well, mathematically, it turns out that the unbiased estimator is to take the sum and divide it by n minus 1. Okay, so if I divide by n, it's not going to be a huge difference, but it's going to be using that particular formula. It provides us with what we would call a biased estimator. So we want an unbiased estimator, and that's dividing by n minus 1. I mean, if you think about the procedure, they're basically a mean. Variance is a mean. It's the mean of the squared deviations. Okay, but in the population, I want the mean of those 8 values. Okay, in the sample, I want the mean that best represents, using those 20 values, that best represents over 4,000 values. So you can go through a mathematical proof that shows that the expected value of this, the sum of xi minus x bar squared divided by n minus 1, is equal to the population variance. You couldn't do that if you divide by n. So that's why we divide by n minus 1, and obviously standard deviation is square root of that. And we don't need that many. Okay, and then the coefficient of variation is the standard deviation divided by the mean. So many of the measures, the calculations are the same, but there's a huge difference here. Well, I mean, it's a slight difference, but it's a big difference in terms of understanding, population versus sample. So make sure that when you're calculating a sample variance, that you divide by n minus 1. Okay. Now, notice that Excel here, I have some statements here, some functions that you can use in Excel, and these are for checking your answers only. Well, once in a great while, maybe I'll have you do a problem where you can use these, but typically I want you to be able to go through the calculations yourself. And but just maybe to check your answers, you can see that there's this var.s, stdev.s. Those are the sample variance and standard deviation functions, whereas for population it's .p for population. Now average doesn't matter. Average is the same. Okay? So then finally, looking at why is this important? Why do we need to have some understanding of this variance and standard deviation? Well, let's say we have a city, and we know that the population mean income is $50,000. Okay, and then let's say that we found out that the standard deviation in income is 1,500. Okay, so I've set this up here to put us 1 standard deviation below and above the mean, 2 standard deviations below and above the mean, and 3 standard deviations below and above the mean. So if you looked at the notes and the textbook, there are a couple of ways to maybe interpret this. Let's assume that the population of incomes are normally distributed, and that is, they're bell-shaped. And so what we would have here is a very defined area, and we would say that 68.3% of all the households have incomes between $48,500 and $51,500. 95.5% have incomes between $47,000 and $53,000. And almost all of them, 99.7%, have incomes between $45,500 and $54,500. Now that's fairly telling versus, let's say if there's another city, $50,000 mean income, but their standard deviation is 15,000 rather than 1,500. Well, now, even though the mean is different, so if we were only given the mean, you might have a very similar thought of what those two cities were like if you were told that their mean income was $50,000. But you need to know, obviously, the distribution. Now, ideally, you would have a frequency distribution or a histogram or something like that, but that's not always available to us. So the standard deviation is helpful in understanding what's going on. And again, if we assume a normal distribution, we'd say that 68.3% of all the households have incomes between $35,000 and $65,000, 95.5% have incomes between 20,000 and 80,000, and almost all have incomes between 5,000 and 95,000. Two very different distributions, even though their means are identical. And so the standard deviation is giving us a lot more information. The same can be said about Chebyshev's theorem. The Chebyshev's is just, well, what if we don't know the distribution? Let's say it's not normally distributed. Well, that's fine. Basically, there's this formula, 1 minus 1 over k squared, where k is the number of standard deviations. So let's say it's 3. What we would say is that at least 88.89% of the households are between 5,000 and 95,000 in income. Okay. You calculate it for 2 standard deviations, 75%. So at least 75% of the households have incomes between 20,000 and 80,000. And of course, if we made that 1,500, we could interpret it as at least 75% had incomes between 47,000 and 53,000. Okay, so Chebyshev's theorem is very helpful, as well as the empirical rule. Not everything is normally distributed, so Chebyshev's is a nice theorem to use. You can't use it at 1 or below, but anything above 1 you can get an idea of what's going on. So if you have any questions about these, how to calculate variance, standard deviation, coefficient of variation, understanding these rules here, please let me know.